Hey everyone, welcome back. In this lesson, we're going to be talking about the atmosphere. So, of course, we're going to be focusing on the Earth's atmosphere. I'm going to throw in a little bit of spacey stuff just for fun in the middle. But in this video, we're going to be discussing a few different aspects of Earth's atmosphere. Um, so, we'll talk about things like uh, how thick the atmosphere is, and what the atmosphere is made out of, and things like that. And then we'll go into a couple of different sort of more subtle points about the atmosphere. The first one is humidity, and the second one is clouds. And at some point a bit later on in this course, when we're discussing weather and climate and stuff, then we'll discuss things like precipitation. I was going to throw a little bit of that in here, but instead I opted to add a whole bunch of pictures. So we'll do that instead in this one, and then we'll discuss precipitation at a later date. So the first point that I would like to make is that compared to the rest of the Earth, the atmosphere is incredibly thin. So this picture on the screen doesn't really make a lot of sense if you haven't seen the video that I've taken it from, but this is from a Vsauce video, which if I remember this when I'm uploading it, I will add a link to this video in the description. Um, but so in this video, Michael, this guy, he highlights that the atmosphere, while it might seem quite thick to us, like on a human scale, it's reasonably thick. It's on the order of tens of kilometers or maybe hundreds, depending on where you choose to sort of draw the the boundary between the atmosphere and space. Um, but in terms of planetary scales, it's really, really thin. And so the picture I've taken here is from the moment when Michael here is describing that if the Earth was as big as an apple, then the atmosphere would only be as thick as the skin of the apple right there. So to give you a sense of scale, that's what he's trying to do here, right? He's trying to give you a sense of scale that if your Earth is this big, then the atmosphere is something like the thickness of the blue line that I just drew. So like if the Earth is this entire thing inside, then the atmosphere is only as thick as pretty much that blue circle itself, um, and everything inside of that would be the rest of the Earth. So like what I'm saying is, if this whole thing in here is the Earth, then the atmosphere only extends out this much more from the Earth's surface, which is not a very big amount, right? This tiny, tiny fraction off the surface is the extent of the atmosphere, and it starts to get progressively thinner. So while you might find that the atmosphere extends a little bit farther, maybe not quite as far as that arrow, but even if you find that the atmosphere extends a little bit farther than you expected, it gets thin really, really fast. So the upper atmosphere, while it's still technically part of the atmosphere, is really thin and basically looks and feels like space. Like there are parts of the atmosphere where if you if you sent up a hot air balloon uh, and asked it to continue rising, then it could rise up to that point. There's still air there, but you in the hot air balloon would probably need a spacesuit type thing just to breathe. You'd need you'd need all of this fancy stuff because one, there's not enough oxygen for you to breathe, but also the atmospheric pressure goes down. And so for us down here on Earth's surface, we're built to withstand the weight of the atmosphere on us, which we might not feel like it's anything because, well, it's air. But if you took the human body and just chucked it out into space without a spacesuit, our bodies are built to resist the pressure that the atmosphere applies to us. So if that pressure is removed, then everything goes all out of whack because we don't have the force of the atmosphere weighing or pushing back on us um, the way our bodies are designed to push out against. So um, As you go into the upper atmosphere, that becomes a problem, even though you're still technically within the confines of Earth's atmosphere. So here's just another way to get a little bit of a sense of scale. This picture that you can see here is of the Earth, and the sun is just peeking through over over the horizon, if you will. So this right here, hang on, let me draw this in like in blue. Actually, no, let's not do it in blue because I don't want it to mess with the blue that's in the picture. So this right here, all the way up to the edge of the black, which I'm trying to steer clear of so that you can see the blue without me covering it up to the extent of that black curve, this is the Earth's surface itself. So if you were looking at Earth from space, all that black stuff and everything down here is all in Earth's shadow, and it's part of the actual solid Earth. The little blue thing, this little blue arc, light bluish white kind of arc up here, is the Earth's atmosphere. So you can see, you can get a bit of a sense of scale that, you know, if I kept on with this curve of the Earth, that it goes something like this over here, and perhaps something like this over here. And the atmosphere extends no farther than about, like, well, maybe not quite that low, but it extends no farther than about this blue curve over here. And I've actually drawn that blue curve to be too thick. So like if the Earth is this giant green thing down here, that all of this in here is the Earth, then what we get is that the atmosphere's height relative to that is only about this much in here. This kind of really, really tiny amount. Now, of course, I haven't drawn this perfectly. This is just to give you an idea of how thin the atmosphere is in comparison to the planet. And then if you imagine that for us, our, you know, tiny, tiny humans, tiny people, tiny cities, everything down on the surface, we think the atmosphere is huge, and it's a challenge to get up a few tens of thousands of feet. But on a planetary scale, that's absolutely nothing. And the atmosphere itself is almost non-existent when you look at the planet from a distance, because it's so, so, so thin. Now here's another example of an atmosphere. This is a way that scientists are able to take pictures of atmospheres from behind the object that they're looking at. So in this picture is the atmosphere of Pluto, and this is similar to what we just saw on the previous slide for Earth, but this is sort of a more complete picture. So like for the Earth one that we were just looking at, we were looking at a section that's maybe like this big on Earth. So we were seeing a section of the surface, and we were seeing a section of that atmosphere arc. So we were seeing a little bit of this, and we were seeing a little bit of this. And this one, while it's not of Earth, it gives the same kind of idea because we're still seeing the object itself, which is the big black circle, and then we're seeing the atmosphere around it, which is this over here. And you can kind of see from this picture that as the sunlight is passing through the atmosphere, you can sort of get a feel for how thick the atmosphere is in different locations. So like if you're looking right next to the surface, if you're looking right in here, if you're looking right down there, right next to the surface, you can see that it's really bright, presumably because a lot of the sunlight is passing through a denser part of the atmosphere. So more and more of that light is getting reflected back out into space, which we can see as we look really, really close to the surface. But then out here, there's a really you can see if you're not sitting at the right angle with respect to your screen, you're gonna have to move around a little bit. But up here, there's still a little bit of blue. There's still a little bit of blue in that atmosphere. So it extends out a reasonable distance from the surface. Now, of course, keep in mind for Pluto, it's a really, really small object. It has a very, very weak gravitational pull compared to Earth. So the atmosphere isn't weighed down as much by Pluto's gravity as it would be on Earth. So for Pluto, that atmosphere, um, when it forms, Pluto's atmosphere sort of comes and goes with the seasons. But as that atmosphere comes during Pluto's summer, it's easier for those gases to reach higher and higher altitudes above the surface of Pluto because of the weaker gravity. So it's not exactly the same as Earth, but this just sort of gives you an idea of what we were seeing on the previous slide, but in sort of a whole, you can see the whole object here instead of just a tiny section of it. But even for Pluto, you can see that the atmosphere isn't that thick compared to the actual object. And then compare it to what we saw for Earth on the previous slide, and you can see that Earth's looks so much thinner compared to the size of the planet. So to give you some numbers, our planet, Earth, has a diameter of just under 13,000 kilometers. So we've got a radius of this much right here, 6,370 or 71 kilometers. So that means that our planet, here's Earth, right? Our radius is, so that's this much, is 6,371. So that's the distance from the center to the surface, 6,371. And then the atmosphere is only a few hundred kilometers thick above that. So if this thing here is 6,000, and I asked you to draw something like, if I asked you to draw about 600, so like if I asked you to draw something that's about the 1/10 the size of that, you might extend out this far, right? That's maybe a tenth of this radius that we see here. So we might see that, this thing in here is maybe about 600 kilometers if this radius is 6,000. But the thing is, the atmosphere isn't even 600 kilometers thick. It's really only a couple hundred, a few hundred. You'll see numbers vary depending on where people choose to sort of cut off the edge of the atmosphere. If you look at the different layers of the atmosphere, the outermost one is the exosphere, and that extends out pretty far, but the atmosphere is really, really thin, and it's effectively like you're in space. So it's not like you could fly in a plane at that kind of level. And we'll actually see in a slide or two where all of the activity that we see in the atmosphere, the clouds, the planes, all of that stuff, where all of those things actually occur within the atmosphere. So if we're saying that this little black tick mark right here is the height of 600 kilometers above the surface, and the atmosphere is even less than that, then you can imagine that the atmosphere only extends out, maybe this far or even less, right? I can't get much closer without just hitting the surface that I've drawn there, but you can see that the atmosphere is really, really thin compared to the whole planet. And once again, you can see that down here. Here's the Earth one that we saw a couple of slides back, and here's the Pluto one we saw on the last slide. So you can pause this and you can take a look at, if we could see the entire Earth in this picture, how big would the actual sphere of the Earth be, right? If you tried to draw it out the way we were drawing it out a couple of slides back, if you extended out this sphere, because it's going to go a long way, right? I mean, that green line is probably a little bit too straight, but you get the idea, right? The planet curves something like this, and then the same thing over on that side. Pluto, you can see the whole thing, and the atmosphere looks thicker, but again, we talked about how that's because of Pluto's weaker gravitational pull on the atmosphere that's surrounding it. For Earth, with our much, much stronger gravitational pull, you can see that if the sphere is this big, the atmosphere is really, really, really thin, and it's so thin that if I tried to draw Earth the size of this thing, if I wanted to draw the atmosphere in realistically, I would basically just be overlapping stuff that I've already drawn, right? I'll just end up drawing the atmosphere right over top of the surface because it's that thin in comparison. So from this we can see that basically the point that I'm trying to drive home here is just how thin the atmosphere really is compared to compared to the size of the planet. And when we look at other planets in the solar system, we see some that have really, really thin atmospheres like Mars, and we see some that have really, really thick atmospheres like Venus, and then the gas giants, don't even get me started. They're basically balls that are pure atmosphere, essentially, with a small solid core on the inside. But we can see that for us, all of the things that we need in the conditions for the atmosphere, it's all a really, really thin shell of air surrounding the planet, and we depend on that a lot. And all of the things that we're doing with, greenhouse gases and things with the ozone layer and all of that, it's all affecting that really, really thin layer of our planet. That if you looked at our planet from a distance, you wouldn't even notice that it has an atmosphere. It's not the most prominent thing that you see, aside from the fuzzy edges to Earth in some pictures, and in these pictures where it's sort of backlit from the sun over there. Um, but yeah, so that hopefully gives you a sense of scale. Let's take another look at this from a slightly different angle. So here you can see that we've got sort of the layers of the atmosphere kind of laid out down this left side. So going up here is increasing height. So we've basically got the surface down here and space up there. And this is sort of showing, this diagram here on the left is showing where different things can sort of be found in the atmosphere. So some of it is just labeling the different layers of the atmosphere. So things like the troposphere and where the ozone layer is. Oops, I completely wrote over the word ozone. So the troposphere and the ozone layer and the stratosphere and the mesosphere, all of that stuff that's going on over here. The thermosphere, and this is what I was talking about a little bit before, the exosphere, and this is at a height of 480 kilometers. So if you choose that, maybe you cut off the atmosphere before the exosphere, because it just kind of keeps going and gets thinner and thinner, and I don't think it has a particularly defined edge to it. If you say that this is the end point for the atmosphere, 480 kilometers above the surface, then that's really not a lot, which we could see from our previous pictures and the numbers that we were looking at before. Um, and as you can see from this picture on the left, some stuff that we tend to think of as being way out in space are actually taking place within the atmosphere. Now, of course, things like meteors, they glow because of their interaction with that atmosphere, so that's not necessarily a surprise for those of you that are that have done some reading on meteors and stuff before. The aurora, that's a product of interacting with our planet's magnetic field, but again, probably not super surprising that it's something that happens within our atmosphere. But something that might be surprising is the fact that a low orbit space shuttle is pretty low down in the atmosphere. That if you consider at least up to here as being the entire atmosphere, and the space shuttle is orbiting at this height, that's pretty low, right? That's showing you that it starts to look and feel like space pretty high up, or well, pretty high up for us, but pretty low down in the atmosphere as a whole, right? If the atmosphere ends here and all of this, I shouldn't have done that in green. Let's go over that in black. So if the atmosphere ends right here and all of this feels like space, then for all our practical purposes, the atmosphere is way thinner than 480 kilometers, right? The 480 kilometer mark is up here, and we're going to see in this image on the right that all of our activity takes place way down here in the bottom sort of 80 kilometers is and honestly even lower than that. 80 kilometers is just the cutoff for the thermosphere to the mesosphere. But then we're going to see now, turn your attention to this image on the right. You can see that here's again the mesosphere that we see over here. That's the cutoff between the stratosphere and the mesosphere right there. And then down here is the stratosphere in this area right here. And this ranges from 10 kilometers down at the bottom to almost 50 up at the top, so up to 48 kilometers there. And you can see that our activities all take place within this stratosphere. You know, we've got an upper limit for military aircraft, we've got weather balloons, we've got storm clouds, we've got passenger planes. So this is sort of probably the big one, is where do planes fly in the atmosphere compared to everything else. Even the ozone layer is pretty low down in the atmosphere. It's around this 19-20 kilometer mark above the ground, which is not really that high. That's like two Mount Everests and a little bit. We can see Mount Everest over here for comparison. And with the storm clouds, which we'll see a little bit later on, the clouds themselves, the bottom of the cloud is very close to the ground, but the vertical size of that cloud, that height of the cloud is tremendous. And that's something that we don't really see because we're down here on the ground and we're looking at, just this enormous, the base of the storm cloud, and we don't really appreciate how high up that goes. But you can see that a lot of our activity, all the things that we're concerned with, happen way, way down in the bottom section of the atmosphere. And you can see that this picture on the right is really just a tiny, tiny section of this picture on the left. It only goes about this high, and all of our activity, everything that we're basically concerned with, aside from people in the space stations and or people who are working with the Hubble Space Telescope and stuff like that, all of our activities take place in a pretty narrow range of the atmosphere, ranging from between 0 and honestly not even 50 kilometers above the surface of the Earth. So think about that if you've got a planet with radius, the physical size of the planet from the center to the surface is 6,000 kilometers, and if you go from one end of the planet and dig through the Earth to the other end of the planet, that's almost 13,000 kilometers. The atmosphere being only about 50 kilometers on top of that, as far as we're concerned, is a really, really thin blanket of air. It's hardly even a blanket. It's like a sheet of thin air that starts to get even thinner the higher you go. Not so much in this picture, but in this picture, the higher up you go, it starts to get thinner really quickly. So hopefully that gives you a good sense of scale for the size of the atmosphere. So now we're going to talk about the composition of the atmosphere, and this isn't going to take particularly long. I do have another 12 or so slides to get through after this, but a lot of them are pictures. So we're just going to talk for a few more minutes, and then I'm going to show you some pictures of some clouds. But first, the composition of the atmosphere. So one interesting thing to note is just how much of the atmosphere is composed of nitrogen. We always think of when we're talking about our breathing, we talk we need oxygen to breathe and we breathe out carbon dioxide. But if you look at the stuff that we actually breathe in, sure, it's true that we need the oxygen, but when you look at what we actually breathe in, we breathe in a lot of nitrogen and we breathe out a good amount of nitrogen as well. So it's obviously, it makes sense to say that we breathe in oxygen, we breathe out carbon dioxide, because oxygen is the thing that we need, so we need to get that in, and carbon dioxide is the thing that we don't need, so we need to get that out. But if you look at the composition of the air that we breathe in versus the air that we breathe out, it can be a little bit surprising to see just how much of that air is nitrogen. We actually breathe out a decent amount of oxygen as well, but that's something that you guys can look up on your own time. From this, you can basically just see that the atmosphere is mostly nitrogen and oxygen. If you add up those percentages right there, that's already 99%, right? The 78% nitrogen plus 21% oxygen, that's 99% right there. and the remaining 1% is everything else that you'll find in the atmosphere, which if you look here, the next sort of biggest player is argon, and then you can go down the list on your own time and find some of the others. For those of you that were in the Zoom class this week, this was an example I gave you of a type of test question I could ask where it's something I haven't explicitly described in our lectures. So, for example, we're studying here that nitrogen and oxygen are the two biggest components of the atmosphere, and argon is next. And a test question where I ask you guys to do a little bit of research, just so that I know that you aren't all working on everything together, is find the fourth one, or the fifth one, or the sixth one in the list. So if nitrogen's number 1, oxygen's number 2, and argon's number 3, what's number 5? That's the type of question that I might be able to ask you on the test, where I expect you to go and do a little bit of reading yourself, and then come back with an answer and tell me where you got that answer. Cool? Cool. So that's about it. That's kind of all I wanted to mention about the composition of the atmosphere, is just how much of it is nitrogen. So the next thing we're going to talk about for just a couple of minutes is measuring humidity. And the reason I bring this up is because for anyone that keeps track of the weather, you might often see the weather app or the weather channel or whatever talking about humidity and maybe relative humidity and what's the difference between the two, and if it's a percentage, if they say relative humidity 70%, what does that mean? So what I want to quickly explain in this section is how that stuff sort of works. So if you look at the slide here, it says that warmer air is capable of holding more water than colder air. So that basically means that if you take a little packet of air, a little parcel of air, so let's say, since I'm already drawing it, let's say we have like a little cube of air, and that air has some weight to it, right? It has some mass of air in there, which is not very much because air is pretty light. But what this point here is saying is that the warmer the air is, the better it is at holding on to water in the form of water vapor. So warmer air is capable of holding a good amount of water vapor. So the parcel of air, the packet of air itself, is made out of nitrogen and oxygen and stuff, right? Composition of the atmosphere. But the warmer the air is, the better it is at holding water vapor within it. So when we're talking about humidity, we're basically comparing the weight of the air compared to the weight of the water vapor that it is hanging on to. And we're not going to go into how they measure the amount of water vapor, like by mass and stuff, but we're just going to talk about the calculations that you'll see on the weather channel and stuff. So if you need to convince yourself of this fact that warmer air is capable of holding more water than colder air, the most humid times of the year in a colder country like Canada tend to happen in the summer, when the air is warmer and it's more capable of hanging on to onto moisture. So you could either think of a cold country like Canada in the summer versus in the winter, or you could look at a more tropical country, for example, the Dominican, where there's, instead of a summer and a winter, there's a wet and a dry season, and the temperature changes in that range by a little bit, and the humidity changes in that range as well. So now when it comes to looking at the stuff that you'll see on the Weather Channel, we're going to need to introduce this new concept, which is called the saturation specific humidity. That's this thing right here. So that's telling us the maximum amount of water that like a little packet of air can hold. So this cube of air right here has some maximum capacity, just the same way that airplanes have a maximum weight load for, passengers and baggage and that kind of stuff. Same thing with a packet of air, a parcel of air, that's trying to carry moisture, that's trying to carry water vapor. There is a maximum amount that it can hold, and that amount depends on the temperature, right? Warmer air is able to hold more water, which means that this saturation specific humidity is uh, is higher, right? It's able to hold more water um, if it's warmer. So as the temperature goes up, the saturation specific humidity also goes up. You don't have to memorize that word. If you want, you can call it the SSH or whatever. Or you can just call it the specific humidity, and we can drop the word saturation. So if we're talking about the specific humidity or the saturation specific humidity, same thing. That's just telling us the maximum amount of water that that packet of air can hold. And as I just said, the warmer the air is, the more water it can hold, so we can see that this specific humidity depends on the temperature. Now, when it comes to doing the actual calculation, the relative humidity, which will be given as a percentage, takes into account the temperature of the air, because that tells us what the saturation specific humidity is. And then somebody goes out and measures the actual humidity. And I don't know all the details of exactly how that's done, so we're not going to talk about it. But whoever goes out and measures the actual humidity, the calculation for relative humidity is taking the one they measure, the actual humidity, dividing it by that sort of calculated value for the specific humidity, and then turning that into a percentage. So obviously this right here is a fraction. When you plug in a bunch of numbers and throw it into your calculator, it'll spit out a decimal, and then you take that decimal and you multiply it by 100 to get a percent. So so let's look at an example of that. So this first point tells us that at a temperature of 20 degrees Celsius, the air is capable of holding 15 grams of water for every kilogram of air. So if your block of air, right, our cube from the previous slide, if your parcel of air, your packet of air is 1 kilogram. So if you've got 1 kilogram of air in here, that amount of air is able to hold 15 grams of water vapor inside of it. So for each kilogram of air, it's able to hold 15 grams of water within that packet at a temperature of 20 degrees. So the thing with the 20 degrees thing is that basically there's this graph where you've got temperature over here. So let me write T E M P. So we got temperature on that vertical axis. Or no, sorry, I've done this wrong. Sorry. So let me draw both axes. So we've got temperature down here, T-E-M-P. So we've got temperature down here, and we've got the saturation specific humidity up here. Oh, that's terrible. So we've got the saturation specific humidity up here. And basically what this looks like is, so if we're at a low temperature over here, cold air is not very good at holding a lot of water, so it's going to have a low saturation specific humidity as well. So we'd have a point somewhere around here. And for a really high temperature, that's going to be really good at holding water, so it'll have a really high saturation specific humidity up there. And the way that this goes, if you do all the temperatures in the middle, it sort of looks like this. So, and then that kind of keeps going up. So this black line, this black curve that's going from the bottom left all the way up to the top right up there, this is telling us the saturation specific humidity. So that's telling us that at any given point, so at a point like here, a temperature of, let's say this is our 20 degrees, then we go up, we look right here, oh, okay, there's our saturation specific humidity. We look over here on this axis, and this right here should say 15 grams of water per kilogram of air. So that's how you would use a thing like this. So you've got your temperature right here, which says it's 20 degrees, and then you see where 20 degrees hits on that curve. You look over here at this axis, and right here it'll say 15 grams per kilogram. So the 15 grams is 15 grams of water per kilogram of air. Like so. So that's how that kind of thing works. So your humidity, if the air isn't holding that full 15 grams, then maybe it's holding something down here, and then you can use that to calculate your relative humidity. So if the actual water content of the air is at that blue dot instead of up here at the specific humidity curve, then you can see there that there's a difference between how much water the air is holding compared to how much water the air can hold. Now, if that graph doesn't make sense, don't really worry about it. That's just for those of you that are sort of interested in looking into something like that. But basically, we know that from this graph, we get that at a temperature of 20 degrees, the air is able to hold 15 grams of water for every kilogram of air. So 15 grams per kilogram. So we know the temperature of the air is 20 degrees. That's what we're told. And from that 20 degrees and this thing down here, we can figure out that its specific humidity is 15 grams per kilogram. So when we look at our equation for relative humidity down here, we know the value for this saturation specific humidity, which we can see over here has been filled in, 15 grams per kilogram. Now, for the actual humidity, somebody goes out and measures the actual humidity of the air, and they find that it's only 5 grams of water for every kilogram of air. So we get that it's 5 grams per kilogram. 5 grams of water for every kilogram of air is the actual humidity. So that's what goes in right here, and we can plug that in right here. So we've got 5 grams per kilogram over 15 grams per kilogram. Don't worry about the units because the units are the same thing. So when you divide, those will go away. So like if you had like meters divided by meters, the number you end up with is just a number. There's no measurement attached to that. There's no meters or centimeters or anything attached to that. So because the grams per kilogram thing is the same up here and down here, we can just sort of ignore that. And then we just look at these numbers. Our relative humidity is going to be 5 over 15, but we always see it on the news as a percentage. So you look at 5 over 15, well, that's the same thing as 1/3, right? We're still leaving it as a fraction for now. That's just reducing it to its lowest terms as 1/3. As a decimal, that's 0.333, and so on. And the bar above the 3 means that that 3 repeats forever. And then to go from a decimal to a percentage, we just multiply by 100. So you get that the relative humidity is 33.333333%. So I know that's a little bit abstract because of the stuff with the graph down here. It doesn't necessarily make a lot of sense if you haven't worked with such things or thought in that type of way before. If you haven't tried to gain information about the world from a graph like this, it can be a little bit confusing. So don't worry about that too much. But hopefully this gives you some idea now of how these humidity calculations work. So if you take a look at such a table, and then you see on the weather that the humidity is 70%. If you look at the table and you figure out, okay, well, the temperature's 27 degrees, so 27 is like here. So if I go up, then it should hit the saturation curve right here. And then if I go across, that's going to tell me what the specific humidity is over here. And I don't know what that number is, so that's something that you could look up. And then, so that would tell you what the saturation specific humidity over here is. And they've told you the 70% part, so this part you know, So you could use that to figure out what the actual humidity is, because you know this quantity over here and you know this quantity down here. So you could calculate the missing one with just a little bit of math. So yeah, there you go. Cool stuff. Let me know if any of you try it. So now we're going to move on to talking about clouds. Now I know that this lesson has already gone on for 40 minutes, so don't worry too much. The rest of this is basically just looking at pictures after another slide or two. So what we have here is just a little bit of information about clouds, basic stuff. We know that clouds form when water on the surface of the planet evaporates. So we've got water, in the ocean or in a lake or just, moisture somewhere on the ground. And as it heats up, for whatever reason, that's something that we can talk about at some point as well. As it heats up, the water evaporates. So it turns into water vapor, it rises up. Now the air gets cooler the higher you go. So it's not going to stay water vapor forever. And then at some point, at some height, it condenses to form a cloud. And that's pretty basic stuff. We already knew that. So the water vapor rises and then it condenses. So it goes from being vapor to little droplets and forms clouds. Then those droplets eventually form drops, which fall as rain or possibly snow or hail or whatever. Now the different types of clouds that form can be affected by a whole bunch of different things, like the conditions in the atmosphere in that particular place at that particular time. Perhaps the landscape around them affects whether clouds form more or less frequently in an area. So for example, things like deserts and mountains and the rain shadow effect and all of that. Climate patterns that carry moisture to different parts of the planet regularly versus parts of the planet that don't get very much water. Once again, similar to that whole desert argument. So lots and lots of things that can factor into where clouds form and what types of clouds form. So now we're going to take a look at some of those different types. So here are the different types of clouds. Now this might look a little bit intimidating, but let me explain what's going on here before we go through some pictures. So basically over here what we have is the altitude or the height of the clouds above the ground. So if you've got the ground right here, then these two are really the same thing, one like really the same altitude, but one of them has rain and snow and the other one doesn't. But so we've got these low clouds, and then higher up in the atmosphere we have these sort of medium level altitudes, these that are like a middle ground between the low and the super high. And then up here we have the super high clouds that are way up in the upper reaches of the atmosphere as far as we're sort of concerned. So what we and so that covers the altitude bit. Now over here, these words, so horizontal development, whatever that is, basically what that means is that these clouds are really, really wide. So if you had, so you might have a cloud that looks like this. So it's not a very tall cloud, but it's really, really wide, or there are a bunch of really little ones that form one like this. So that's like when the whole sky is cloudy, that's horizontally developed clouds, generally speaking. So basically the clouds just spread out over an area that covers the whole sky. You can't see the sun, or if it's at night, you can't see the moon. The whole sky is just this light gray or possibly a slightly darker gray. And if you could see above that, they're not super tall clouds, at least not in comparison to these guys. The vertically developed clouds are the ones that they might be somewhat wide at the bottom, but they don't have to be. But then as they go up, they just keep going. The clouds, as you go higher up in the atmosphere, the same cloud formation just extends kilometers upwards, which we also saw a few slides back with when we were looking at the scale of the atmosphere. There was a storm cloud that extended from a couple of kilometers above the ground to like 13 kilometers above the ground, up into the up into the stratosphere. So those are the vertically developed clouds. So now if you look at these names, you might see a few patterns. So if you look down this column, this vertically developed column right here, you'll see that all of these have a similar word sort of stuck in there. So what we have here is, let's look at the standard one here, because this one doesn't have any stuff attached to it, doesn't have any prefix or suffix attached to it. So the clouds that are vertically developed, so to speak, so these taller clouds, are cumulus clouds. These are the puffy ones that, you know, if you see an emoji of a cloud or like a silhouette of a cloud on Google, like if you Google like a clip art picture of a cloud, chances are they've tried to imitate one of these. These are the ones that we sort of picture in our heads and see on the Weather Channel and stuff as the cloud that they're showing. So basically, any cloud that says cumulus, so which we've got obviously down here, that's just the name of the cloud. Down here, we've got cumulo in the prefix, so that's telling us it's a vertically developed cloud because of this prefix. Altocumulus, that's telling us it's a vertically developed cloud because it says cumulus, and same deal up here, cumulus, once again. So if you see that word stuck in the name of the cloud, that's telling you that it's a tall cloud. It's one of these guys. It's one of the vertically developed clouds. And then over here in the horizontal development, we see a similar thing, but with a different word. Here we see stratus. That should extend to the S. We've got stratus again. We've got stratus again. And we've got stratus again. So what we can see here is that horizontally developed clouds are called stratus clouds. They've all got stratus in the name somewhere. So the different names tell you whether or not there's precipitation, and they tell you where in the atmosphere you'll find them, low or high altitudes. So just by looking at the name of the cloud, you can see whether it says cumulus or stratus, and that tells you if it's one of the really, really tall clouds or one of the really, really wide clouds. Now, for the rest of the name, we look at these guys, the high, the middle, and the low. And the low with precipitation. I don't know if that's the clearest color, so let me change to... Does purple look very different from the blue that I've been using so far? Yeah, okay, that'll do. Actually, you know what? Let's use green. I think green will be better. Okay, yeah, let's use green. Okay, so let's get rid of that and those. Okay, so now we're gonna look at the row for high altitude clouds. Notice that both of these, they've got different suffixes, cumulus and stratus, but they have the same prefix, cirro, right here. And that's the same thing as cirrus clouds, which you may have heard of, C-I-R-R-U-S, cirrus clouds. And those are the really, really thin, wispy clouds that you see super high up in the sky, cirrus clouds. This is where that prefix comes from. So if you see if you see someone, or you know, like a weather thing that's talking about cirrus clouds in general, then you don't know if it's a vertically developed or horizontally developed cloud, because it doesn't say cumulus or stratus, but you know that it's high up in the atmosphere, because that's what this means. Similarly, if we look at this row for the middle level ones, they've got the word alto stuck in front of them. They've got the prefix alto stuck in front of them. So we've got altocumulus and altostratus clouds, which are just cumulus and stratus, but a little bit higher up in the atmosphere from their basic low versions. So in the lower atmosphere, there is no prefix or suffix. These are sort of the standard, if you will, that cumulus and stratus clouds, they have the simplest name when there's in low altitudes and there's no precipitation. And then if they're in the lower atmosphere, but there's also precipitation, then we add nimbus to the cumulus cloud, and we add nimbo to the stratus cloud. So we can see that this thing is pretty much the same in both of them as well. So if you see nimbus or nimbo, that's telling you that there's precipitation. If you're seeing alto, that's telling you it's sort of a middle level altitude. If you see cirro, that's a really, really high altitude cloud. If you see cumulus, that means it's a tall cloud. And if you see stratus, that means it's a wide cloud. So that's sort of how these different names work. There are some subtleties to it, and you could ask a whole bunch of different questions about the clouds that don't have names that match any of these. But this is sort of just an overview of a few different cloud types and how the naming system sort of works. So now we're just going to wrap up. Let's look at a few pictures of these different clouds, and we're going to go in order. So we'll start here with cirrocumulus clouds, and then we'll look at these four, and then we'll look at stratus clouds and look at these four. So you'll see in these pictures, hopefully you'll get a little bit of a sense for how these clouds all kind of look the same, but they get lower and lower in the atmosphere. And then same deal that these clouds all look the same, and they just get progressively lower in the atmosphere. So let's take a look. So first up are our cirrocumulus clouds. So if I take red and just put a circle around that. So we're looking at these ones right now, cirrocumulus clouds. So you can see that they are those kind of puffy ones. You can't really see that they're tall clouds per se. You can't see that quote-unquote vertical development. But you can see that they're puffy clouds. They're all kind of separate from one another, but not really, I guess. It's hard to say much about it without comparing it to one of the other ones. So for this one, just note that it looks like they're all really high up in the atmosphere, although it's hard to get that kind of context without being able to see anything else. But these are high up in the atmosphere. They're those puffy clouds that we sort of tend to think of when people say the word cloud. Let's move on to the next one. So now we're looking at altocumulus clouds, these ones here. And if you look here, once again, it's hard to get an appreciation for whether it's lower or higher in the atmosphere, but take my word for it that altocumulus clouds are a bit lower down in the atmosphere. Once again, you can still see that they are that puffy kind of nature, and once again, this picture doesn't do a great job of showing that they're tall clouds per se. That's more of a technicality. It's not something that you really have to worry about, since in practice we don't tend to see that very much. But yeah, just something neat that you guys can think about the next time that you're looking at the daytime sky. Now here's your picture of a sort of standard stereotypical cumulus cloud, and you can see that it has that shape that we tend to associate with clouds, that it goes like this and then up like this. It's got that kind of cloud type shape. That's really hard to see in that color, but like you can see that it's got this kind of shape to it, right? Which is the shape that we seem to associate with clouds more than the ones that we're about to see, right? It's got that same sort of puffy kind of, it's not a super flat cloud, which is why these are the tall clouds, but it's got that same puffy type look to it, right? And these are sort of these are the standards for the vertically developed clouds. So it's hard without a sense of scale. These are not particularly small clouds. I don't know the actual number for it, but this distance is probably not particularly small for the height of the cloud. A characteristic feature that you can kind of see if you look down here is that they all look like they've got a really flat base, that they have a really, really flat bottom to the cloud, and then it gets puffy as you go higher and higher up in the cloud. So that's just something sort of interesting to note about these clouds. But yeah, so that's sort of the standard cloud that we picture. But the altocumulus and cirrocumulus, when you're watching this video, you can go back a couple of slides and sort of compare these to each other. But for now, let's move on to the last one for the vertically developed clouds. So this one's a bit hard to see. This is a cumulonimbus cloud. These are the ones that we associate with thunderstorms and stuff. So let me highlight this. Let's see, does orange show up well on this? Okay, that shows up pretty nicely. So let me trace out this cloud. So we can see up here that this is all part of the cloud, right? You can see that this is all part of our cumulonimbus cloud, and it actually extends over here that we can't really see in this picture because it's cut off because of the way I've made the PowerPoint. Sorry about that. Here's our cumulonimbus. But then as we're coming back, this is all actually part of the cloud. All of this in here is all part of the cloud as well. So you can see here that this is possibly the best example of a vertically developed cloud. This is a huge, huge, huge cloud that is capable of, if you look at the right pictures, you can see that it looks like it covers like an entire city or even considerably more than that sometimes. And if you put that into scale, if you put a city in a space of that size down here, this is a tremendously tall cloud, right? So this gives you this really drives home that idea of vertically developed clouds. But yeah, so this is still a lower atmosphere type thing. Altocumulus and cirrocumulus clouds would form at higher elevations or at higher altitudes. But this really drives home the idea of the whole thing I've been saying about tall clouds. So now let's move on to the last four. I know this lecture's almost been an hour now, so feel free to watch it in chunks. I should have said that before. But um, yeah, let's move on to the last four now. So here are cirrostratus clouds. So let's circle that in our little chart over here. So cirrostratus clouds. So these are the ones that you might see on really, really pleasant days. Generally, any type of cirrus clouds are indicators of good weather, but particularly these ones I find, at least where I am, these ones are strong indicators that pleasant weather is here or on the way. Generally, I mean, you won't see these if the weather is particularly unpleasant because the storm clouds form at lower altitudes, so you wouldn't be able to see these ones. But anyway, these are cirrostratus clouds. You can't really see, once again, you can't see that they're super wide clouds per se, but hopefully you can get some sort of context, or if you compare these to what you see outside right now or later this week, hopefully you'll be able to compare and see, oh yeah, okay, those ones do look like they're way higher up in the atmosphere than these other ones. So give that a try and let me know what you guys see. Next up is altostratus clouds. So here you can really gain an idea for what I mean by wide clouds. So these are this is just a massive formation of stratus clouds that extends way off into the distance, right? If I'm drawing a little like 3D type arrow, these extend way off into the distance there, right? And they cover pretty much the whole sky. It's a little bit, you can see a little bit of the sky over here and stuff, but for the most part, these clouds cover the whole sky. Once again, it's kind of hard to tell whether they're higher or lower than other ones without having gone through all four already. But the next ones we're going to look at are stratus clouds. So right now we're here at altostratus, and now we're going to head down to looking at stratus clouds. So for stratus clouds, this is what I mean by when the whole sky is just gray. It's those really dreary days, rain or no rain, when the whole sky is gray and you can't see any blue sky. These are stratus clouds. They're really, really wide and they're low in the atmosphere. Once again, because this whole sky is gray, it's difficult to see that they're low in the atmosphere, right? These could have been super high up in the atmosphere and still cover the whole sky, and it wouldn't look very different. But trust me, stratus clouds are lower down in the atmosphere. Um, and now we're just going to take one quick look at the last one. There's not really much to talk about here. It's more of these are what the clouds kind of look like. go out and look at the sky yourself and see if you can identify any of the clouds you see as one of these 8 types. But let's look at the 8th one now. So here we go, just as we reach the hour mark for this lesson. This last one is the nimbostratus. So this is a stratus cloud, so a wide cloud that covers much of the sky, that also has with it precipitation. So clouds that are about to precipitate tend to be darker. So cumulonimbus clouds tend to be dark, and nimbostratus clouds tend to be darker. So stratus clouds might be white or a light gray. Nimbostratus will be gray, a darker gray to almost what we would describe as black clouds, like the one in the picture here. So it covers a huge amount of the sky. So it's a wide cloud, and it's dark, and that's indicating precipitation. And maybe there's some signs of precipitation over here off in the distance. There's sort of some stuff that looks like it's sort of coming down from the cloud there. But yeah, that's just an overview of these different types of clouds. So I know this was a really long lesson, so when I post this, I'm going to make sure to give you guys a heads up that it is long and that you can feel free to watch it in chunks if you wish. This is, I believe, I will double check and let you guys know ahead of our Zoom class, but I believe this is the last lesson in this unit for geography. So the quiz slash test, whatever you want to call it, will cover material that we've done up until the end of this video, but nothing beyond it. So you might have questions on the atmosphere, you might have questions on clouds, but whatever I post after this for geography will not be on your test for this unit. But if you have any questions, let me know. Once again, feel free to watch this in chunks, so don't feel bad, and rewatch it if you need to, because there was a lot of information in this one. Yes, that is the end of our lesson for today. I will see you all in our Zoom class next week, but I will also see you all in the next video. Have a good one.